Welcome to this unit where I want to simply explain how, when you see a specific exercise in the general context of statistics 2, you know which of the different approaches you heard about is actually to be used. So when we start with this, the first thing we can do is take a look at some specific keywords or key facts in the exercise itself. So for example, if it either says total probability or base something, this usually hints at probability theory, calculating with probabilities. Usually it doesn't say so, however. Usually you have to go roundabout way with this, and one of the ideas to find out this is on this topic would be that a lot of probabilities are given. So probability of events that, for example, take place one after another, or probabilities for two or more events. So whenever you see something like this, a lot of different probabilities, this hints you have to work with probability theory, with the probability calculation formulas. A bit more on which of the different formulas to use when, that's on the next slide, so on slide 3. Then the next big topic is on distributions. So usually, except for maybe the normal distribution, doesn't really say so much this is on this and this distribution. So how do we know whether this is on any distribution at all? Well, either if it says like normal distribution or distributed so and so, or you read something with replacement. There's also a point where we go into more detail in one of the next few slides. However, you directly know this is about one of those exercises when in the task you're asked about one specific probability. So something like this and this should be exactly this many, at least this many, at most this much. That's usually a pretty good hint it's in some way related to those distribution exercises. Here we have two slides, one for the discrete distributions and one for the continuous. So we are also going into more detail in this topic a bit later on. Then could be that you're asked to provide a confidence interval or range of acceptance. Here there's basically nothing else surrounding this. So in this case, it's relatively sure that you know what you have to do because it usually reads directly confidence interval. However, here as well, I want to go into a bit more detail which of the different versions of the confidence intervals you should use in which context. Then, whenever you read something about a margin of error or about the probability to trust something, which usually is around 90 something, like usually it's 95, or you have some alpha value for an alpha error. This is usually related to some kind of test. So in the slide 7, we go into more details on which test to use when. Then finally, you might read something about regression, but whatever is about regression also relates to the testing part. So we cover this in this part as well. So what we can then do first is consider the part on probability theory. And here the first thing is if I have like event 1 or event 2 occur or take place. When it's with an or, what you might have to use is the addition theory. If instead of the or, you clearly have an and, so both events should have already taken place. So both things should have been realized already. That's the multiplication theorem. Then, could be that one of the events already has taken place. One of the different things already occurred. And the question is asked about the probability of the second event happening. This results in some problems related to conditional probability. Under the condition that the first event has happened, what is the probability that the second event will happen? So we have one event or another, one event and another event, already both haven't taken place, or one event haven't taken place, second not yet. Then, and here it becomes a bit more in-depth, you could use the theorem for the total probability or Bayes theorem. So first, for the total probability, you know that you have to use the formula for this. If many single events are described, and you know that only one of them can take place at any time. So for example, it's like your customer buys one of 3 products and only one of them. The customer orders one of 5 different menu choices, but only one. The customer visits one of 5 stores, but only one of them. And there's no more than the menu choices you offer, no more restaurants. So all the possibilities are listed. You have a share, how many customers, for example, buy product 1, how many product 2, how many product 3. And all of this adds up to 100%. So you cover all there is, and there's no overlap. Customers only use one of them, buy one of them, visit one of them. So when you have this and conditional probability, so for example, the customer visits one of 5 restaurants, and you have the share, how many customers go to each of the restaurants. And for each restaurant, you also know the probability that a customer will be happy, that a customer will leave a good review. This then tells you total probability, like good review, chance for each restaurant, and you ask, in general, what is the probability that someone will leave a good review? So that's total probability. The theorem of Bayes, that's what you use when you more or less, let's say, switch the condition around. So before you have A under the condition B, and now for some reason you want to have B under the condition A. That's where you use Bayes' theorem. That's also the idea, you know, in earlier examples or in the text, you have one conditional probability given, and now you're asked again for a conditional probability, and it's the exact flip side of what you had before. That's a good indicator for you to use the theorem of Bayes. Okay, so that's already the main part in the context of probability theory. We could add final one, the De Morgan rules. That's if you have 2 combined events with the or and the and you want to have the opposite of both of them, that neither 1 or 2 takes place. That can be, in some cases, be simplified by using the De Morgan rules. However, that's not so often the case as the other ones before. But however, this is, again, if something like this occurs, that's a neat way to actually make it a bit easier, a bit shorter. Okay, so that then finally was actually everything on probability theory. And we can switch to distributions and start with the discrete ones. So the first question you should ask yourself, is there more or less replacement taking place or not? What do we mean with this? Well, it's usually with you select one object and then either you put this back or you do not put this back. If you put this back, we call this replacement. So if each object can be selected more than once, that's replacement. If each object can only be selected once, that's no replacement. Thereby, with binomial distributions, which is what you have to use when you have replacement, the probability will always remain fixed. So in this case of exercises, there's a pretty good chance that in the exercise itself, you have the one probability which is relevant in this context. If you have no replacement, you need to know the population size and the size of the group in the population with the characteristic you're looking for. So that's like a pragmatic approach. Now, one thing, if you only have a probability, you can only use binomial distribution. If you have population size and group in the population with the characteristic you're looking for, then you could use hypergeometric distribution. Not necessarily does this mean that you have to use it. As I said, only when there is no replacement. So if everyone can be selected only once. If one of the elements could be selected more than once, then you can use the two sizes you have, divide one by the other, and you get a probability you might need for the binomial distribution. So that's the first two we might consider here. Then, when the question is about the first occurrence of an event, so what's the probability that if you throw a dice, the first one you get on the 5th throw, or that the first one occurs after 8 throws. That's an indicator for geometric distribution. So if it's about the first occurrence of an event. If on the other hand you're asked about rare events, that's an indicator for Poisson distribution. With rare events, or with the Poisson distribution, you also have to have the mean or the variance. That's the interesting thing here. With Poisson distributed variables, mean and variance are equal. So if there's something on this area, this is a clear indicator for the Poisson distribution. Well, that's the most common discrete distributions. We could add the uniform or rectangular distribution. That's if all the different events have the same probability, like throwing a dice. Each of the different outcomes has the same probability. However, that's not listed here. That's listed on the next slide under continuous distributions, because the uniform distribution could be either discrete or uniform. With the continuous version, however, it's problematic to say, yeah, each event has the same probability. So yeah, we could say the density function is actually a constant. However, this is a bit clearer to understand if you're been given a clear beginning and a clear end. A dice can result in values from 0 to 6. If you go to a bus station, you don't know when the bus comes, but only that the bus arrives every 20 minutes. So you're asked about how long you have to wait, or what's the probability of waiting more than 50 minutes. There you have a beginning and end. The waiting time is not less than 0 minutes, so the bus arrives when you arrive, and no longer than 20 minutes. You barely missed the bus. So here you have an end and a beginning. So that would indicate uniform distribution. It's not a perfect idea, but it's a good indicator. Then, if it says something about, yeah, what happened in the past does not matter. So, for example, you have the question, your computer on average breaks down every 2 hours. What's the probability that it will break down in the next 5 hours? And it says, doesn't matter how long the computer already has been running. That's an indicator for the exponential distribution. This also means you need to have a mean or an indicator or a parameter lambda. So this is similar to the Poisson distribution, as in you need the mean, or you need this parameter which results from the mean. Or, different idea to actually have this. This means also that you have an exponentially increasing or decreasing probability. So if you also know this, because it's listed somewhere in the exercise, might also be an indicator for having an exponential distribution. And then, finally, we have the normal distribution. Here, it's either listed as this variable is normally distributed, or that's where you have to have a mean and the variance or standard deviation given in the exercise. So you have both of those, and it says nothing specific. Well, this is strange, but you might assume this could be normal distribution, but usually it should say it's normally distributed, because, well, only mean and standard deviation doesn't necessarily mean it's a normal distributed variable. So the exercise would be a bit off if you only have those values and no info on the normal distribution. So that was already everything there was on distributions. So we can go to the third part. And the third part was on confidence intervals. So here it's relatively straightforward. You have to use confidence intervals. Question now is, do you have an information about the variance or the standard deviation? And the exercise says something about a confidence interval for the mean. So the keyword here is mean or means. Then, if you have the variance or the standard deviation, you can use the Gauss version or the version using the Z distribution. If you don't have the variance or the standard deviation, it's still on means, then use the T distribution variant. This is usually also related to you first have to calculate variance or standard deviation from the data you have. So because you have to first calculate this, you have to use the corrected version of the standard deviation. This means T distribution variant. However, in both cases, it's the keyword you have to read. It's a confidence interval for the mean. If the keyword, however, is variance, that means you have to use the confidence interval version for the variance. Well, that's the three possibilities you're given here. Confidence interval for means, either with given variance or with unknown variance, and confidence intervals for the variance. Okay, so this only leaves us with the final part on tests. That's actually the biggest part, because here we have actually three different sub-parts. The first is, do you actually have a value and you're asked about, does your data set, whatever, imply a divergence from this given value? That usually results in comparing means. Here the question again is, do you know the variance, the standard deviation? Then you can use the version for the known variance, so based on the Z distribution. So you run a Z test. If it's unknown, you first have to estimate the variance, standard deviation, and then you use the t-test version, or the comparing means version for unknown variance, which basically means you use a t-test. There could also be the version that you have to compare two samples, whether they have the same mean. This would be a two-sample t-test. That's not listed here in specifics, but this could also occur. This, however, requires you to do a lot of work to get the common standard deviation. So this was the first part, comparing means. The second part starts here with chi-square tests. And, well, for chi-square tests, for relations, you need two variables. So in some way, you need to know there's two variables. And the text should read in some way something about relation or association. Another good indicator is, you know that the variables are nominally scaled, so you basically have a contingency table or can construct a contingency table. So if it's something like this, this indicates going with a test for stochastic independence. If you have only one variable and a given distribution, and you should test whether this one variable, this one sample, has this distribution you're talking about. This means a goodness of fit test. So usually the variable is given as a nominal variable, Could also be ordinal with different groups or classes, but it's usually not metric. And you have a data table. So whereas for the test for stochastic independence, this is based on a contingency table, this here is more or less based on the frequency table and a distribution for each of the different groups or classes. So this is comparing one variable, one sample with a given distribution. If you have two groups, two samples, and are asked about, do they share a common distribution? Do they have the same distribution? That means you have to go with the homogeneity version of running a homogeneity chi-square test. So you see that's the second group already. First group, differences, comparing means, so Gauss test or t-test. Second group, chi-square test, so either stochastic independence, goodness of fit, or homogeneity test. And then the third part, that's in relation to regression analysis. Here, we're basically faced with two aspects. So we could start with the keyword regression and something about explanatory power. That would be the f-test. Or with a question with regards to the whole regression line, quality of the whole model you're faced with. This is always f-test. If you're only asked about specific coefficients, that's again a t-test. Here it should say something about regression and it should say something about coefficients. Also, for the t-test, for the coefficient test, you need to have, well, first of the coefficients, second of, you need to have or calculate the standard errors for the regression and for the coefficients. As this is quite a lot of work, usually those standard errors should also be given in the exercise. And well, same thing for the f-test. Here you also need to have or have calculated before or calculate now the coefficient of determination, because this is needed to get your test statistic for the f-test. So those are two additional indicators which of those two tests with regard to regression you're asked to do. And well, this then already concludes, well, this third part, the testing part, or fourth part with tests. And this also concludes this whole unit on which approach to use in which context. So I hope you enjoyed listening to it. I hope you learned something from it, got a better understanding what to do when. And well, if you want to see exercises where this is actually used in, you can visit the rest of this course or have a look in the corresponding playlist. I say goodbye and see you next time.